20 minutes and then
22. No,
20. You said 20.
20. No, 20.
20 and then it rings and then 5 minutes.
If you finish earlier, it's fine.
Okay.
No problem.
No, you said 20 and then it rings and then I have 5 more minutes.
No, 22, you have 3 more minutes to wrap up and then 5 more minutes.
I'll finish maybe a few minutes early. Okay.
No problem. Okay, go.
Okay, so today we're going to see a paper about the mitral cells, what computation could the mitral cells do. This paper is written by Restrepo. I think he's a student of Richard Axel, no?
Restrepo?
No? Ah, I thought he was. So, a good person. He wrote this paper and it's about the mitral cells. So first let's remember what the mitral cells are. So as we saw in class, the mitral cells are the second level in the pathway. The first station is olfactory, epithelium, it's the olfactory receptors. They send their axons to the mitral cells, who are the second station, and these mitral cells send their axons to the cortex or to other different places. Okay, so it's very important to remember that this is only the second station after the sensory input. So we'll start with the goal. What is the goal? What is the question of the paper? So the question is, what kind of computation could this second station, these mitral cells, perform? So the simple thing that they could do is the order identity. They could identify what kind of order is it. I don't know if it's alcohol or coffee or whatever order is it. But the more complex thing that they can do is maybe they can understand what is the value of the order. For example, is it a rewarded order? Is it associated with something good? Is it a rewarded or unrewarded? This is a more complex task to do. Not only to identify what the order is, rather also to understand if this is the rewarded order or unrewarded order. So this is the question we're going to ask. Can the mitral cells do something complex like this? Okay. So in order to do that, they do this experiment. This is a discrimination experiment. So how it works, I'll explain. This is a go-no-go task. I'll explain shortly what they do. So the mouse puts his nose in the order port, and he gets an order. Then comes the stage where he needs to decide if this is a rewarded order. If he thinks it's a rewarded order, he needs to lick 4 times, and then he gets water. Okay? And if it's an unrewarded order, he doesn't lick, and then he doesn't get also water. So the task of the mouse is to learn if this order is rewarded or unrewarded. At the beginning, he doesn't know, so he'll do by chance. After a few blocks, a few trials, we'll see that he will learn this is a rewarded order because I got water in the previous trials, or this is the unrewarded order because I didn't get water from the previous task. Okay, the task is clear. These are thirsty mice, so they really want to get the water. So they learn pretty fast how if it's a rewarded order or it's a unrewarded. No, that's a good question. There's no punishment. Sometimes they put it, when there's an unrewarded order, they put on a puff, something like that. And here there's no penalty, but they still can learn without the penalty. Okay? So here's the time course of how it works. So around time 0 comes in the order. Then it's the response area. He needs to decide what kind of order is it. Is it rewarded or unrewarded? And if it's a rewarded order, he gets the water and the water rewarded, period. Okay, so he needs to decide. If it's rewarded, he needs to lick. If it's unrewarded, he doesn't lick. The task is clear. He needs to learn to discriminate between rewarded orders and unrewarded orders. And we do it many blocks, several blocks. Every block is 20 trials. In these 20 trials, 10 out of them are rewarded, 10 are unrewarded. So each block, there's 10 times where he will get water, 10 times he won't get water, and we have several blocks. As more blocks come, he can learn what kind of order is this. So for example, this is a simple graph of the behavioral. What happens? So you can see at the beginning of the first 2 blocks, it's random. He doesn't know what kind of order, is it a rewarded or unrewarded? See already, I don't know, for graph 6 or even 8, you can see that he already learned. Here's the percentage of correct. How many was he right? If he identified if it was a reward order, so you see from block 6 or even 8, he really gets it very good. He has a behavioral skill.
What's the percent correct is out of the time he should have licked, or also avoiding the licking?
Also avoiding, that's good. We will touch it in the next slide, what kind he was right, but here he was correct. He licked when he was supposed to lick, and he didn't lick when he wasn't supposed to lick.
Both types of errors are treated the same.
Yes. So soon at the end, maybe last time, I'll explain what happened in these different areas. But for now, correct means that he licked when he was supposed to, or he didn't lick. It's called a hit. He licked when he was supposed to, or correct rejection. He didn't lick when he wasn't supposed to lick. Okay, clear everybody understand? So the mouth can do it. The question is how he does it. How does the brain activity work when the mouth learns to discriminate? So in order to do that, we need to record from the mouse's brain, from the mitral cells. And here we see a recording from 3 different channels. Okay, it's a multi-unit recording. So we have multi-units recording at the same time. And from, for example, from channel 5, channel 1, and channel 2. This is just spontaneous spike, let's say. So if we look and zoom in, we can see that there are some synchrony between the different channels, different neurons. So for example, you see here the black neurons over here and over here between 5 and 2. These are synchronized spikes. You see it also here. This black are synchronized spike between channel 5 and channel 2. And for example, between channel 5 and channel 1, you can see the red these red spikes are the synchrony between different channels. So there is some kind of synchrony between the different neurons, and maybe this kind of synchrony is what does this, is involved in the learning task. Yes.
So it's tetrals or
It's eight channels, different channels, and they record sometimes it's single units if they're
Multi-unit.
yeah, multi-unit. Remember with the 8?
It's one electrode and several which record from several neurons or several electrodes?
No, 8 electrodes, no?
Yeah, many electrodes.
Right? 8
The shaft and printed electrode on it.
And each one records from seven nearby neurons?
or a single or yes.
Each channel.
So I won't go into the spectrum. Sometimes it's a single unit, it's from a single neuron, or sometimes it's like from an area, they call it a multi-unit. But for our purpose, you can think of it as a single neuron. The first row is from a single neuron, and the second row is from a single neuron.
So what does the red and black represent?
So this is synchrony between, let's say, for example, let's say this is the first neuron, okay? And this is neuron number 5, neuron number 1, and neuron number 2. So you can see the synchrony between 5 and 2. These are these 2 rows. You see there's a synchrony between the spikes.
So the difference between the red and the black is that the red is both the 1 and 2 and the black is 1 and 3?
Yes, if you call them 1, yes. 5 and 1 or whatever you mean. Okay, it's between the first 2 rows, and the black is between the first row and the third row. Yes?
Just to make sure, this is the spontaneous.
Yes. So this is spontaneous. Yes, so soon we will see exactly. Yeah, so what happens to the synchrony when he learns the task? Does it change or it doesn't change? Okay, everybody understand the different? So you can think of it as different units. And you can imagine that these spikes don't occur exactly at the same time. So they need to define like intervals that we call them synchronized spikes. So each spike that happens within less than 250 microseconds, these are synchronized spikes. Okay? So synchronized spike is spike where they have a different, in a different unit, they have a spike that is synchronized within 250 seconds, microseconds. Okay, so what happens? What happens when they learn to discriminate? So what we see here is this is a recording. All of these is a recording from one single neuron. And you can see it's divided into different blocks. It says blocks where he learns. So the first block is before he knew the order, and the last block, the ninth block, is when he knows what kind of order it is. So you can see, and here at the red is when he needs to decide. So you can see that as the blocks go, he learns. There's an increase in the firing rate of the neuron. See it? Over here it's less excitation, and here it's more excitation. Meaning that something about this excitation happens when the mouse learns how to discriminate between the rewarded order. What happens in the unrewarded order is there's like some kind of inhibition. You see it over here? There's less spikes in this area than at the beginning, and here there's more spikes in this area. Okay? So this is from a single neuron, okay? Single neuron, each row here is a different trial in the same block. Each block has 10 trials. There's different neuron, and we record it, and we see that in the ninth block, in all trials, there's more excitation in this area. When the order, it's the red thing, okay? Yes.
He should decide later.
No, here he decides. Here's the decision time.
So 0, I mean the learn fires.
So here is when the order is given, and another. What?
When you do the processing?
Yes. He smells like around over here. I think it's really over here. So, and then we record. We check what happens when he needs to decide if it's rewarded or.
These two are the same mirror.
Yeah. Yes.
So actually we
You
see
should
here
say.
that the same, no, it's the same mitral cell.
Yes. I said they don't say exclusively, but you could think of it as the same mitral cell.
So if every mitral cell is supposed to be sensitive to one kind of odor, we can also say we can say a couple of things. We can say that maybe this odor was odor A in this case.
Okay, that's a good question. That he's responsive to order A and not to order AB. We will test this in the next slide.
He's learning better.
Yeah.
We can think of.
So you're saying it's because of order A, that's why he fires more? Or because
Maybe.
okay, so that we'll see in the next slide. But for now, I just want to point out, because it's a little bit confusing. What we see here is only the synchronized spike. Okay? It's very important. Here, this row, each row, is only the synchronized spikes that we saw before. Okay? It's not all spikes. It's a little bit confusing.
Synchronized with other.
With a different unit.
So for each unit, you choose only the spikes that are synchronized.
Only the red
any other
spikes.
unit.
Yes,
Only
exactly.
the ones with an asterisk. Either
Yes,
red or black.
you're right.
Why?
It means that there is like more synchronization.
Exactly,
Not necessarily
exactly.
there
That's what it
are
means.
more.
Okay, you understand? So it's only synchronized spikes. So the information, the excitation is what happens is only the synchronized spikes. Soon we'll see what happens if we consider all spikes. Now I'm telling you that this is only synchronized spikes. There's an excitation in the synchronized spikes. Okay, it's a little bit confusing.
Not only pair-synchronous, right?
What?
Pair. not
Yeah,
pair.
so here we're looking at one neuron, and each spike here has a pair that it's synchronized to. Okay, we're looking at one neuron, but each spike here has a pair that is synchronized. Okay? So the information here, the excitation is only the synchronized spike. No. So what we said, excitation to the rewarded order, and inhibition or less excitation in the unrewarded order. Here we just compare, for example, block 1 and 2 and 7 and 8. Here's before he learned and here's after he learned. And you can see, compared here, you can see really there's more excitation in the 7-8 blocks compared to the first, second block. So there's
excitation, right?
what?
Right.
So it's excitation and the synchronized spike. It means that there's more synchrony. You're right. What do I mean? You see that there's more, the fine rate here is larger than the fine rate over here, right? It means that there's more synchrony. It's a little bit confusing, eh?
The synchronized firing rate is increased.
Exactly.
Not
It's confusing.
increasing the firing
Okay? But it's true. Increase in fine rate and the synchronized spikes, it means there's more synchrony. As far as you can think, it's more synchrony over here. Yes? Everybody understand this confusing point? No, they don't write it. It's just very confusing. Okay? We'll see later why it's important. And here we just compare, for example, here they took the synchrony. You see, as the blocks go, there's more synchrony or excitation in the rewarded than in the unrewarded. Okay? And here you see the behavioral. You see that, as we said before, that from block 6, it could perform the task very well. And in the same time, there is more synchrony for the rewarded and less synchrony for the unrewarded order. Yes? Everybody understand? So this is the first conclusion. An increase in fine grade or in synchrony for the rewarded and a decrease for the unrewarded. Now, it gets a little bit more complicated. It's a little bit complicated, but it's very nice. It's worth understanding it. So what do we see here? Let's start from the x-axis. This is the delta z. Delta z is a score that tells us if it's an increase in the fine grade or a decrease in the fine grade. Okay, a positive delta z means that it's an increase. Over here means an increase in fine grade, and negative delta z is a decrease in the fine grade.
Synchronized firing rate or?
Okay, so that's a good question. So the black, it's very important. This solid line is when we consider only the synchronized spikes. Remember those red or those black spikes, we only consider them. And the broken line is when we consider all spikes, not only the synchronized spikes. what we can see here, the y-axis is this is the cumulative, the percentage of the trains, for example, that have this number of delta Z. So 50% have over here, what the delta Z is 1. It just tells you the fraction of how many of them have a positive or a negative delta Z that increase in fire. So let's start with the solid red line. The solid red line is when we consider only the synchronized spike. And we can see that almost in every trial, almost in all times, there is an increase in the firing rate when we consider only the synchronized spikes. But if we look at all spikes, not only the synchronized spikes, we don't see that. For example, if we look over here, this is a broken line, we see that sometimes there is a decrease in the firing rate and sometimes there is an increase in the firing rate. So the information is only in the synchronized spike. Only in the synchronized spike there's an increase, but in the total, if we look at all spikes, there isn't not always there an increase or a decrease in the firing rate.
This is a CDF, right?
Yes.
So it's up to
1.
delta Z equals 2 is 1, right?
Yeah, I guess or something like that.
Okay.
Why does it matter?
So,
Uh, So does everybody understand the difference between the solid line and the broken line? The solid is when you consider only the synchronized spike, and the broken line we consider everything.
You have a good audience, Dave, don't worry.
No, I look at their faces.
No, they're very smart and they're not shy.
Okay.
Okay, so if
Not
you
everybody.
understand, they ask, don't worry.
Okay.
Don't
Well,
waste time on,
okay. So we see the black,
understanding it.
the blue. Yeah, they do. The blue one is from the unrewarded order. Here again, we consider only the synchronized spike. So we see that almost always there is definitely a negative, and if we consider all the spikes, sometimes, mostly there's a decrease in fire rate, but sometimes there is also an increase in the fire rate. Okay.
I just want to know if they wrote in the paper, how do they get this idea of synchrony?
How?
Just, it sounds like it's
No, there's something known about the synchrony of the mitral cells. It's something known. It's not that they.
in relation to the rewarded or unrewarded.
Yeah, so I don't know. They have a paper before when they didn't look at the synchrony, they just looked at the firing rate, and then they didn't find it. But here they look at the synchrony. I guess that it's known that something.
The history is an LFT. There is a very, very
LFT.
strong synchronous rhythm in the olfactory valve. Nobody knows what the purpose is.
So they checked it, what's the correlation between this and this?
Okay. So why is this graph amazing? Because if you take this vertical line, a delta Z equals 0, you can really discriminate between if it's a rewarded order or if it's an unrewarded order. For example, if I get a positive delta Z, I know that this is a rewarded order. And if I get a delta Z that is negative, I know that this is an unrewarded order, almost in all cases. So if I look only at this, I get this measure, this delta Z of the synchronized spike, I can know what kind of order it is. Like if I can read the brain of the mouse, I see this delta Z, there's an increase in the fire rate, I know this is a rewarded. I can predict that this is a rewarded. I see a decrease in the fire rate, I can know almost for sure that this is an unrewarded order. This is amazing. Do you understand that?
Did they test it? I mean, did they test this model on
I don't know. I would do that, but they didn't do it. That's what I would do.
on their data? It's like okay, but
No, but you see, it's almost in all cases there's a delta Z. They ran in the discussion that they can do it, but they didn't do it. I don't. It's amazing. Like read the brain. You see this delta Z, this measure, and you know if it's a rewarded or unrewarded. Okay. Okay.
Did they say about the broken line? Did they say why it's more biased towards the rewarded? Meaning
Yeah,
it makes
that's
the broken line-
yeah. It's a very big. I don't know. It really disturbs me. Why this?
Yeah, because the
broken-
unrewarded in the broken line does have some information.
Exactly. So what I asked to do that. He told me that I guess the information is not only in the synchronized spike. There is some information to consider all spikes, but it's not that pure as you could see in the synchronized spike. It's more information than if you have all the spikes. Okay. It's a good question. Okay. Wow. So here's for your obvious question. I think so. Now we will try to switch the orders. We will do that order A is rewarded, order AB is unrewarded, and then we would switch it to do the order A is unrewarded, order AB is rewarded.
With different lights?
What? I think it's the same one.
Same.
one. So what they see that it's not related to the order, rather to the reward. It seems like excitation is here in order A and here it's in order AB, and it's related to the rewarded and not to the identity of the order. So I'll do this and then I'll jump to conclusion. So as we said at the beginning, we could have 4 different possible responses. We could have a miss, hit, that means he licked when he was supposed to lick. A miss, he was supposed to lick, but he didn't lick. A correct rejection when he didn't lick when he wasn't supposed to lick. And a false one when he licked when he wasn't, he licked when he wasn't supposed to lick. And we could look at the mistakes. What happens in mistakes? For example, we have the miss, where it's a rewarded order, but he didn't lick. What is it similar to? Is it similar to the behavioral, meaning that he didn't lick, meaning there was a decrease in the fine grade because he didn't lick, so we would expect there to be a decrease? Or is it like a hit, where there's an increase in the fine grade? Okay, so he missed. It's something in the middle. He missed, it means he didn't lick, so we expect that decrease. But on the other hand, it's a rewarded order, so we would maybe expect that there's an increase in the fine grade because it's a rewarded order. Just say it fast because you're a good audience. So what the results are, that for some reason the hit is exactly the same as the miss. Meaning that also in the hit and also in the miss, there is an increase in the fine grade. Although he didn't lick at the end, the information is there. There's an increase in the fine grade, meaning that he knew it was a rewarded order, but for some reason he didn't lick. But the information is as if it's a rewarded order. Okay.
So this means that the wrong decision was performed in a later.
It's amazing, right? Like he knows it, but he didn't do it for some reason.
No.
What?
No.
No.
The brain doesn't know.
No, the micro cells know, but I don't know. He has like a free will and he decides not to. I think. No, I don't know why. Maybe the cortex ruins everything. Okay. So I'm jumping. Conclusions. I have 2 minutes to do. Okay, I'll do the conclusion. So what are the conclusions? These are personal conclusions. What I learned from this paper. First thing is if we compare it to the visual system, we can see that in the auditory system, these are the micro cells are the second station after the receptors. If we compare it to the visual, we get these are like the bipolar. Yeah, it's easier, right? The bipolar cells that they are the second station in the visual pathway. I don't know. I always thought that these bipolar are very stupid cells. They don't do anything very complex, but you see in the olfactory system, it's so nice that even the second station can do some kind of computation, not just pass the information to the next station. This is the first thing. The second thing is what we said before, I won't repeat it, that we could put this vertical line in the middle and we could really predict or know what kind of order, if it's a rewarded order or if it's unrewarded order. And the last conclusion, this is a little bit hard for me to admit in, but I guess I have to, and that it's not only cortex. So we have computation that is outside the cortex. Not all the computation is inside the cortex. Huh?
You said it was hard for me to admit.
Yes, it's very hard for me to admit, and I guess it's true. It's against what I was educated, but I guess it has to be true. So you can see it in the name of the paper. Associated cortex features. These are things that we think happen in the cortex. That's what I always thought. But we see that it doesn't happen only in the cortex. There are also other places that are important for doing computation. Thank you. Question?
Do we know what, for the microcells send their projection to a lot of areas? What are the areas from which they receive feedback that can help create this kind of behavior?
So it's
It's an implanted question.
So I jumped on this. There was one slide about the neuroadrenaline.
Noradrenergic input.
Noradrenergic input to come from where?
Locus coeruleus.
Locus coeruleus.
Huh?
And it sends back these neuromodulators that they some way they make this more synchrony, and then there comes the information that there is that this is a rewarded order.
But rewarded is something with dopamine. They didn't check it.
I don't know. They check noradrenaline.
Okay.
I don't know. Maybe it's also dopamine.
First of all, we have dopaminergic interneurons in the olfactory organs, right? As well, it's actually the second most occupied region with dopaminergic neurons. But in this paper, they just said no more
Okay, so it's something about the,
But
they
there
don't know
aren't
why.
any other
How do they get this?
projections that contribute.
How should, why only know adrenergic A?
Huh? Only know that.
They checked a lot of things in this.
No, they
No,
check
they check,
only
no,
the
no.
odor.
How do they know? They know about biology.
They
Yeah,
didn't
Not
know
really
how, but
no
they know.
modulatory systems. And noradrenaline has history in the literature to be important in learning, and that's why they tested.
Okay. No, but he has like the 3 papers before that he does, so they know stuff.
Maybe everything.
They know, you know.
Yeah, they
What?
know stuff.
No,
They
maybe
know.
everything has an influence.
What?
Maybe.
They tried a lot of things.
So
I'm
But
saying
they
this-
stay with what they know.
Maybe
Maybe
not.
not so special.
Maybe not.
I know, I don't know. But the noradrenaline is involved, they know that. But they, I don't know. What else? More questions?
Um, the temporal pattern of the micro cells, they usually tell information, share information about the order identity. And if they synchronize more, how
How do they have the identity? That's a
they
good
not lose
question.
the order identity?
That's a how do they know the order identity?
When you say synchronizing, so they're firing at the same time. So how
How do they have the information about the order
yeah,
identity? So I don't know, they don't say anything in the
did
paper.
they check like after he learns whether it's rewarded or not? Did they also check to see that the order identity is still high?
I
or
didn't see
it's
that
not?
they checked that, that's a good thing.
Maybe it's not the temporal code at all.
Yeah, yeah, I don't, you know that,
That's what's my theory.
it's true? I don't know.
Oh yeah, that's the bon ton. The new bon ton now, which is led by Dina Rimberg, is that and Andreas Schaefer, is that the information about the odor is about shifts
Identity?
within the sniffing cycle. But he will tell you.
Ah, okay. So
If
you
I know the answer to this question, how does synchrony contribute to the changes in the sniffing rate? No. Maybe there is a connection? Yeah, maybe. That's a good point to think about.
When you think about
Okay, next talk.
Okay.
Do you want to do the thing, push the button?
There's a Gandalf quote that they should have put in the
What?
presentation. When in doubt, always follow your nose.
What?
When in doubt, always follow your nose.
כן, לא, רציתי לקפוץ להראות דוגמאות, אבל זה לא...
עדי, בבקשה. Okay. מה?
צריך להגיד לו. איפה האביזן שלך למסך אחר?
Another screen.
למה אתה לא מתכנן את זה לפני? It's not my computer, I don't know.
Well, I can use a different computer. I can just pull it up on Google.
But I don't know.
Like that. sometimes יש pain, אז לא בא לי. pain אין לו. שיש לא יכול.
There we go. Where's my screen?
אז לא תתקשרו אליו. אבל הבנתי
Okay.
Okay, I can go.
Wait for like 10 minutes until I'm halfway. So this paper is division normalization in olfactory population codes. It's a paper out of the lab of Rachel Wilson, who he has mentioned a number of times. So first I want to talk about the general motivation of what we're, the broad goal of what we're interested in. So in a variety of sensory systems, we have this phenomenon that if you have a neuron which is selective to a particular stimulus, and you present that stimulus, but there are also other stimuli, so the response to that neuron is suppressed. And just as an example of that, this is from the Hebel and Weasel paper that we read together in class. And this is in on-center neurons. So if you flash this bar of light in this area of the visual field, so you see an on response. However, if you flash a larger bar of light, you don't see any response at all, which is kind of strange because this is included in that, so you think that you would see a response, but in fact you don't. And Hubel and Weasel noticed this. They said that from experience with simpler receptive fields, one might have expected wider slits to give increasingly better responses owing to summation. The result was just the opposite. Responses fell off rapidly as the stimulus was widened. So we see we have this strange phenomenon that when you have more stimuli that the neuron doesn't prefer, so the neuron's response is suppressed. So a way to think about this suppression is as gain control, meaning that you're modulating the output of the neuron. So there are two different ways that this could happen. One of the possibilities is called input gain control. That actually what you're doing is that this neuron is receiving input from other neurons, and based on the input from other neurons, it fires. So what this suppression effect does is it suppresses the input to the cell, meaning that it will fire less. The other possibility is output gain control. And the idea of output gain control is that you somehow overall affect the firing rate of this particular neuron, so it doesn't fire as much with any given input. And one of the ways physiologically that we think about this kind of suppression is lateral inhibition, namely that you have neurons with different receptive fields and they are inhibiting each other. So now that we've set up this background, we'll move to the olfactory system, and particularly we're looking at the fly olfactory system. And the reason we want to look at the system is because it's relatively simple. You've seen this picture 500,000 times, but just to go over the idea again, so you have these olfactory receptor neurons. They synapse on projection neurons, and so if you have olfactory receptor neurons that have the same receptors, synapse on a particular glomerulus, and so each glomerulus only receives input from one type of olfactory receptor. So now what we want to quantify, we want to see is how the projection neurons respond to the input by the olfactory receptor neurons. So what they did in this paper is that they found odors to which particular olfactory receptor neurons are responsive, and other olfactory receptors really aren't responsive. Now, most odors in the world aren't like this. So many odors will affect many olfactory receptor neurons, but they chose odors that really only affected one particular olfactory receptor. So what you can see is that there's this characteristic shape. That you have an increase in firing rate of the projection neuron in response to the olfactory receptor neuron input. And then after a certain amount of time, you have saturation. What you see in this graph here, so this case was a little bit strange. They found that the maximum firing rate was lower than the others, so what they did is they applied a GABA antagonist, and they found that this projection neuron was being suppressed. And when you apply the GABA antagonist, so you have an increase back to the normal firing rate of all the other neurons. Yes?
Just what's the method? Is it like multi-unit, in vivo?
So here they're doing in vivo, they're really just recording using electrodes. So you're recording from both the olfactory receptor neuron and also from the projection neuron.
I think it was shown in the previous slide.
Yeah.
Okay.
Yeah, so you're recording both from the olfactory receptor neuron and the projection neuron of belonging to a single glomerulus. Yeah. This is going to get my water here. I can go for like 5 minutes talking without drinking. Okay.
And the red line is to the GABAergic antagonist?
So the red line is when you have a GABA antagonist. So it stops inhibition that's happening in the system. So this case is kind of strange. They don't really talk about it. If you have a GABA antagonist, you should see an increase, and here you have a decrease, but it's not so big, so they kind of ignore it. But this is just to characterize the typical response of these projection neurons. So we haven't done anything really with lateral inhibition yet. In this case, there just happens to be some sort of inhibitory behavior. Okay, so now we want to start to create a mathematical model for this saturation curve. And this is going to be kind of the main character in the rest of the presentation, so it's important to look at it carefully. So what we have here is an equation that models the firing rate of the projection neuron as a function of the firing rate of the olfactory receptor neuron. So R max is the maximum possible value that the projection neuron will achieve. ORN is the olfactory receptor neuron firing rate. And sigma is a little bit confusing, but the idea is it's the amount of input that you need into this projection neuron in order to drive a half maximum response. So the sigma essentially tells you how much input you need in order to have a particular output. So now we're going to have kind of an interactive part. So what happens as we change different things in this equation? So what happens if we change the olfactory receptor neuron firing rate? David?
Yeah.
So essentially, right, you're going along this x-axis, and you increase. So as you increase the ORN, so this thing becomes 1, and so you eventually reach R max. Okay, so that was easy. What happens if you increase sigma? What happens if you increase this guy? Right, so it takes longer to reach this maximum response. Okay, and what happens if you increase or decrease R max? Yes,
Nothing. The
Word.
rate would be the same, but the maximum would be different.
Correct. Okay. So we understand this equation. That's it's very important. So now we're going to do an experiment where we actually look at lateral inhibition. So right now we're going to look at two particular glomeruli, VM7 and DL5 that we saw before, and just look at them again. Right, this is VM7, that's DL5. And the way that this experiment is set up, we have two different kinds of odors. So one odor is a private odor, to which these particular olfactory receptor neurons and projection neurons are responsive to. And then there's a public odor to which other olfactory receptor neurons are responsive to, but not this particular one. And in this case, the odor that they chose was pentyl acetate. And what they did is they presented the private odor and the public odor at the same time, and they wanted to see how the firing rates of these neurons here would affect and inhibit this neuron over here. So what you can see fairly clearly, I think, is that as you increase the levels of public odor, the odor that the other olfactory receptor neurons are responsive to, you get a decrease in the firing rate of the particular projection neuron that we're looking at, meaning DL7 and DM5. And you can see that even as you increase the levels of private odor, you still get this suppression response as you increase the public odor. And what you can also see here is that, so this is if you have just the private odor, you have a strong response. If you add the public odor, you get a suppressed response, but if you have antagonists, all of a sudden you get a larger response again. So this really seems to be some kind of lateral inhibition. So now that we've gotten these results, we want to think about how the lateral inhibition actually happens. So we have the two approaches that we mentioned before, the input gain control approach and the response gain control approach. And so the input gain control model that they presented is that what we do is we add some value to the denominator of this function. And effectively what this will do, as we said before, is that it will take a longer time for the projection neuron to reach saturation. So you add this S value here, and it's similar to increasing sigma. So as ORN gets bigger, you'll still reach the same saturation level. It just takes longer. And this is input gain control because effectively what we're doing is we're saying, again, it's similar to increasing sigma. In other words, you need more input in order to drive a particular response. The alternative is the response gain control model. And what they did in order to formalize this is we simply have a constant that we multiply by our max. And what that does is it effectively lowers the maximum firing rate of the projection neurons. Yeah.
Why does this calculation represent input gain control and the other one response gain control? How do they justify the connection?
Okay, so the idea is, so for the input gain control one, so think of adding S as changing sigma. So sigma, as we said earlier, sigma is the amount of input that you need in order to drive a half maximum response. So adding something to sigma is essentially saying we need more input because some of the input is being suppressed. So that's kind of the idea behind this. And for the response gain control, so if we have a constant multiple of our max, effectively what we're saying is that we have an overall change in the output of this neuron that its maximum firing rate is now different. It's now smaller. So regardless of the amount of input that you have, you'll still get a smaller maximum firing rate. Clear?
Can we go back one slide back?
Sure.
What we see here is a response as function of time, right?
No. Well, I mean, each of these, yes, is a response as a function of time. But
what we characterize as the firing rate is like the average over this amount of time.
no, so sorry, these are firing rate as a function of time. Each of these guys is firing rate as a function of time.
And when we go and we say that the projection neuron's firing rate in the y-axis in the other graph is the average over this, or the maximum of the amplitude, or
yeah. So this is firing rate over the period where you have a stimulus response.
is it the maximum period or the average over this?
So that I think that it might be while the stimulus is actually there, and you find the firing rate average over that period.
I think both change, no? Both the maximum firing rate and the integral under the...
Yes.
Both of them change.
In what situation?
To go to the responses.
Yes.
Here?
I mean, whether the change is in the...
No, the other one.
No, the other one. Real data.
Yeah.
This one.
Whether it's the peak changing or the integral under the curve, but both of them are changing.
Yeah.
Yeah. It can have a meaning, of course, but for our purposes, there is inhibition on both.
Right.
Yeah.
Yeah. That's yeah.
No.
Okay. So these are the two possibilities. Now what we want to see is if one of the models fits the data better than the other model. So here each of these rows is a different glomerulus that we're looking at. So this is each line here is the prediction of this here is the input gain control model, and these lines are the predictions at different levels of public odor. So the lighter line is actually a higher concentration of public odor, which is kind of confusing, and the darker line is less public odor. And so for the input gain control model, you can get the actual data represented by the points, to the prediction made by the model. And here also for the other glomerulus, you also see a relatively nice fit. And in this column here, we have the prediction of the response or output gain control model. And here you seem to have not such a nice fit. You have all these points over here that aren't on any curve. You have points up here that seem to be lined up on the wrong curve. So just to quantify how well these models fit the data, so we have a graph of the mean squared error here. This is for VM7, this is for DL5. And you see that the input gain control model has much less error than the response gain control model for both glomeruli. So it seems that we've definitively shown, I don't know definitively, definitively is a very bad word here actually. But it seems to be that at least in terms of these two models, if you were to decide which one fits the data better, so the input gain control model fits the data better. So the next thing that they did is they wanted to quantify how exactly does this lateral inhibition happen? What features of the population of olfactory receptor neurons and projection neurons, what features can we use to quantify what kind of inhibition or how much inhibition we'll get? So actually what they did was they found the LFP in the area of the glomeruli, and they found that there's actually a linear relationship between the LFP and this S value that we had in the input gain control equation.
This time it's the integral, right? Instead of the mean integral.
So I believe so. I'm not sure.
I'm saying that
Yeah.
going according to the units, not here, but here, right? So if it's millivolts times second, so it should be an integral, right?
That makes sense. So what we see is we can actually find a fit to this value of S based on the integral of the LFP. And there seems to be some constant that you have to multiply by the LFP depending on the particular glomerulus that you look at. So different glomeruli might have different levels of lateral inhibition that you need to see the same level of inhibition. So effectively what we've seen here is that lateral inhibition in the fly olfactory system fits better with the input gain control model than the output gain control model. And we also see that the magnitude of inhibition that we see varies linearly with the population response as represented by the LFP of the other glomeruli. So those are the two main conclusions that they drew from the above data. So now I want to talk about a few methodological issues. In general, with these kinds of modeling papers where you fit an equation to experimental data, so it's sometimes there are certain questions that you have to ask. So one thing that you might want to ask is it possible to find an alternative mathematical model that fits the results just as well? In other words, they have this nice model that had some division, some addition, but maybe you could think of something else, like hyperbolic tangent function, logistic function. So they mentioned in the paper that there were a few other things that they tested. But in the space of possible equations that you could use to model a particular set of data, so it's unclear, at least to me, that just because you find one model that fits your data means that is meaningful. Another thing that I was a little bit concerned about was finagle factors. So if you look back in the initial equation, so you see that all of these values here have this 1.5 exponent. And what they said in the paper was that we use this exponent because it provides the best fit to our data, which it's legitimate if you want to make a predictive model and that particular value that you use works well. But the question is it biologically meaningful to just have this number that you tack onto your equation and then and it fits your data better? So what does that really mean?
It interacts with your biological meaning.
that's true. So that might not be such a significant issue, but I think that it's important to think about what are the meanings of these numbers. Another issue is that is ruling out alternative mathematical models a valid method of confirming a particular model. In other words, so we looked at these two models, this one was better than that one, but does that mean that the one that was better is actually the correct one, or is it just slightly less wrong? Another issue. And finally, even if the model makes correct predictions, let's say that it even makes correct predictions 100% of the time. So does the model really have biological meaning? Can we really say that because this model fits the data, and because there's division in this modeling, and the title of the paper was divisive normalization. So this is kind of a modeling approach that people have started using, that they like to model these kinds of suppression things using division. And the question is, but is the division really biologically meaningful? And it might be, but it also might not be.
So what would make you satisfied?
What would make me satisfied is if there were, in fact, a real biological meaning for everything that's happening in the equation. In other words, for something like the Hodgkin-Huxley model, so I can look at those differential equations and I can say, okay, this is channel opening probability, channel closing probability, and it makes sense with the biology. I think that the kind of model that we have here, while the algebra is nice, we still don't really know what the meaning of the different operations that we're performing are. And so maybe we just have to do enough experiments and then we'll figure it out. But it's something that you need to have a theory in addition to the equation. Yeah.
I think all of this is true to not only to this paper, but to models, and not only to neuroscience, but to models in everything. And you can say everything in here about theory and relativity as well. The speed of light being a finite vector. So I think this is a general problem with modeling, is that you're not sure that actually describe reality.
Yeah. So I agree, and in fact, I have one more. I have one more slide. And I just want to. There's a nice quote by Richard Feynman in his lectures on physics. So he says, try to imagine what makes a drag on an airplane flying through the air. The air rushing over the wings, the swirling in the back, the changes going on around the fuselage, and you can see that there's not going to be a simple law. On the other hand, it is a remarkable fact that the drag force on an airplane is approximately a constant times the square of the velocity, or F equals gv squared. Now, what is the status of such a law? Is it analogous to F equals ma, right, Newton's second law? Not at all, because in the first place, this law, meaning the drag law, is an empirical thing that is obtained roughly by tests in a wind tunnel. The law is the result of an enormous complexity of events and is not fundamentally a simple thing. If we continue to study it more and more, measuring more and more accurately, the law will continue to be more complicated, not less. So I think that this is kind of an important thing to keep in mind when you're designing mathematical models to explain biology, especially very simple algebraic expressions. That just because you have a nice algebraic expression that seems to fit, you have to really figure out if there's biological meaning to it, and if maybe the complexity that exists serendipitously produces something that's easily expressible, but in fact is really more complicated. So yeah, I think I'll close with that. And questions, comments, objections, anecdotes, personal stories, jokes.
Questions, comments? See, Rachel Wilson's paper is always everybody is silent because they completely agree with Okay, let's take 15 minutes. 1:10 is break.
Let's do that. Let's just.
What? The quote?
The video.
or not.
Yeah,
Yes.
that they respond if they
Yeah.
have receptor,
Of course.
they proceed, if
Yeah.
there is no receptor in epithelium, they will not proceed. I don't know if the molecules of cocaine do not have receptors.
Maybe I don't know if you smelled it.
I think they have. Even
They
the
have a
hash
smell.
and the
Maybe they have a very weird
phenomena,
smell.
and these things have smell because
Maybe.
some people smoke
But it
cigarettes.
doesn't have. But the fact that it has or not, doesn't have smell doesn't have to do with the cocaine. The cocaine. The
That is not,
physiological
yeah.
response.
But if smoking is, I don't understand.
The features of the chemical of the cocaine.
Sometimes what happens, and this thing happened, okay, when, like, we were smoking in the group, and there was a girl who do not smoke, but the smoke was so much that even she get high of
Of
hash,
which of what?
hash.
Okay.
So that means when you are taking something and they are activating your
Yes.
olfactory neurons.
Why
So,
did it just whatever was in the environment, the
yeah,
surrounding, came to her nose. So
yeah.
the response was not from the odor. The response was that instead of smoking it herself, somebody else smoked it, and it also got into her
Yeah,
blood system. The fact that she smelled it or not did not have to do with the physiological response to the drug.
so you're saying from the nose to the bloodstream.
Yeah, it's just a way. You have many ways
But it
to reach the
has a
bloodstream.
smell.
So it has smell, but the smell does not contribute to the physiological.
But they are the same molecule.
No, you have a molecule and it has some chemical features.
Yeah.
Only one of the features is smell, right? It also has other features which do not have to do with smell.
Smell is some feature or like.
The molecule can be odor sensitive or
The
not.
molecule, yeah.
Molecule is a molecule. It
Okay,
can be odor
if there
sensitive
is
or
some
not.
molecule,
Yeah.
I can smell it, that means that molecule is getting in via my olfactory system also.
It has some response in your
Receptor.
olfactory,
Like
yes.
this is the sensation.
But the fact that it does or doesn't mean that the physiological response from the yes, you smell it.
But the molecule has the same effect all over the
What I'm trying to say, even if you take this girl and you block the microbe cells in the olfactory bulb, she wouldn't smell, right? She wouldn't smell the drug that people smoke. But she would still feel the same way. She would still feel something response because it doesn't have to do with the olfactory
The
bulb.
olfactory system is not doing anything. It is somehow adding or somehow it is contributing.
Not to the physiological response.
Why? I do not understand.
Because the physiological response of the drug does not have to do. You would have the same physiological or similar physiological response if I would just generate like this, or if I would inhale it.
Okay,
The fact that you smell it or not is confusing.
good luck.
Yeah. Gela? יאללה, היי. טוב. So hello everyone. I will present the following paper, Perception of Sniff Phase in Mouse Olfaction. It's a very straightforward article, as you'll see, and pretty short, so probably I won't use much of my time, and you can feel free to ask questions. The idea is very simple, to study the temporal coding, temporal pattern, which Yair talked a bit about before, in the olfactory bulb. To check its resolution and specifically relative to the sniff cycle. So we'll talk about the sniff cycle, which you probably know a bit about. from Nature, 2011. So the experimental setup, they used optogenetics, as we'll see next. And what they did is, if probably, can you see it well or not so good? Okay. Maybe the light will help. Maybe. So they used optogenetics, and in order, what they did is they did cloning, as we studied in the methods course, and they expressed channel reduction and YFP. The marker that they used was OMP, which is olfactory marker protein. It's a protein involved in the signal transduction in the olfactory sensory neurons. Right, there's no need to talk more about channel reduction and YFP. And they just show here that you see here the olfactory epithelium and the olfactory bulb. So they showed that it worked, and they genetically manipulated those mice. And you can see here the olfactory sensory neurons in the epithelium and the nerve terminals in the olfactory bulb. And they, of course, they use this optogenetic manipulation in order to manipulate and check the temporal resolution, right? Because it's very temporally precise, the optogenetics, and that's what they use. So that's about that. They used mice, had fixated mice, and they had the following instruments which they used. So they had the optogenetic laser, of course, and they implemented it to one nasal cavity. Okay. On the contralateral nasal cavity, they had a pressure cannula, which measured, as you see here, this is the sniff cycle. So what you see as positive is the inhalation, and then you see negative is the exhalation. So we have, right, all the time, in mice, we have a sniff cycle, which goes on all the time. So again, one nasal cavity is the pulse stimulation, the other nasal cavity is the pressure cannula to measure the sniff cycle. They had the olfactometer to deliver the odor, of course, to the mouse. And they had here water rewards, which we'll see in a second. It's very similar to what Yair presented, the leaking in the water rewards, in order to train the mice. So the first thing they did for the mice, they wanted to train them to leak. So that was just train them to leak. So if they leak, they get some kind of, they leak water, they get the water bath, they get the water rewards. And then they wanted to train them to leak to response of odor. So if there is, it's again go no go task. If there is odor, they have to leak. If there's none of it, they're not supposed to leak, and it goes as the following. So you can see here that this final valve, this represents the odor delivery. Okay. So they present some odor in the sniff cycle, as you can see. In a second we'll talk about the optogenetics, but for now, just odor. They present the odor in the sniff cycle, and if the mouse leaks, you see here the leaks, it gets water rewards. Very simple. The same thing you can do, of course, as we'll see that they did with optogenetics. So you can see here in a specific, we'll talk about when they did it, but in a specific time of the sniff cycle, they presented, they photostimulated with a laser pulse, and they used this blue light mask because they said maybe there is some kind, so the mice wouldn't use the visual, as it says, a visual cue, okay, of the laser itself. So they put some kind of mask, a blue light mask, while they're presenting the laser pulse. That's the whole idea. And again, the same thing with odors you can do for optogenetics. You can stimulate the mitral cells, if I didn't say mitral cells, in the, not mitral cells, olfactory sensory neurons in the olfactory epithelium. That's where they implanted the photostimulation. You can stimulate them, and if the mouse leaks, give you a reward. The training is again very simple. The punishment is just to not give a water rewards, and also they changed the inter-trial interval. So if the mice did something wrong, and wrong is like Yair said, wrong is when he leaked when he was supposed, or he didn't leak when he was supposed. We treat it the same. If the mouse was wrong, he has to wait a longer time period to the next trial, in order to get the reward, and that's somehow they try to train the mice. And they were saying some in the article. I'm not going to get into it. When it was, they're trying to change some parameters in order to, because it wasn't so easy to train the mice, but eventually they did. And the first thing that they wanted to show is that the optogenetic stimulation it's good. It holds, and it's a reliable measurement, and it fits kind of the order. So you can see here that these are two consecutive order sessions. Okay, so they did actually more than two, so at least 4 sessions. But you can see here the last two, and you can see after the order, each line is of course a mouse, and you can see that after 2 sessions with order, they presented an order, and they wanted to see the correct response. As you can see, it's pretty high. They presented a laser pulse. They stimulated with optogenetics. And you can see that the first session, maybe there is a bit of a decrease, but the second session is already as good as the order delivery. So that's just for saying, okay, we proved that we can use optogenetics here and it works, and the fraction of correct is very reliable and very good. And this in pink are the channel rhodopsin that genetically manipulated, and this of course is the wild type. Okay, this is the control, and you can see that response to the orders, but of course when they present the laser pulse, it's chance level. So that's just to show that the optogenetic works. Yes. In the olfactory sensory neurons.
In all of the receptors?
Yes.
Yes.
So what exactly did the optical stimulation do?
You just give a laser pulse in a specific excitation wavelength, and you stimulate the olfactory sensory neurons.
Replaces the odor.
Yes.
Ah,
Okay. So just to replace the odor, and they're going to use it to check the temporal resolution of the coding. That's the idea. Okay, so from now on, they proved in optogenetics that we're going to use just the optogenetics and not the order. So from now on, it's optogenetics. And so they wanted, the first thing they wanted to check is the sniff phase discrimination. And the main thing, they wanted to see if the mice can perceive in what time they receive this go no go task. Okay, so what you see here is the sniff cycle. Again, what I said, positive, the green is the inhalation, and this is the exhalation. So this is one sniff cycle, and there is a go no go task. So they do the first task is pretty simple. They train the mouse. To this is a go and this is a no go. So the first 32 milliseconds after the inhalation onset, which you can see here, there is a go, and the mouse is supposed to respond. Okay, respond meaning to leap and get a reward. And when he receives 32 milliseconds after the exhalation onset, it's a no go. He's not supposed to leap. Okay. And the idea is to check whether he can learn, whether he can discriminate this time point, okay, in the inhalation from this time point in the exhalation. And what you see here is the results, and this is the last, what we saw before, the detection, the last detection of the, what you saw here, okay, so this is this last trial by the letter, just to, when they, to detect. And then they're checking the phase discrimination in consecutive sessions, and you can see that after 3 or 4, you can see here the mean and the standard deviation. So you can see that after 4, it reaches pretty much 80%, pretty good relative to they had 2 controls. Sorry, this I'll talk in a second about the control, but you see that they respond pretty good after 3 or 4 sessions, and they can indeed discriminate between the two, between the no-go and between the go, as I just mentioned. The 2 controls that they did were wild type and genetically manipulated, and they checked there's the response to auditory clicks. Okay, so they presented auditory clicks, and obviously it's obvious not going to present, it doesn't have to do anything with the sniff cycle, so you can see here that it's a chance level. But yeah, so that's the control they used. So that's the first thing. And then they said, okay, so mice can perceive this phase discrimination, and they wanted to check what's the time resolution. So what they did is the same thing, but now they changed, they varied the no-go. So they, again, we have a go at 32 milliseconds after the inhalation onset, and we have a second no-go, which they varied from 5 milliseconds to 100 milliseconds after the first um, the first stimulus, and they wanted to check whether how good in time resolution can they differentiate. And you can see here again, those are the different trials. The green is the average, and you can see they are saying that even after 10, although it doesn't really look, but even after 10 milliseconds, the first is 5, the second is 10. So after 10 milliseconds, it's already significantly above chance level. But even if it's not 10, so you can say, okay, 25, it's about 80%, and it's pretty good. So it's a very, right, if we look at the sniff cycle, and this is about 200 milliseconds, so it's about tenfold. It's tenfold shorter, the time resolution relative to the sniff cycle that they're sensitive to. And it's, it's pretty temporally precise.
Pretty? This like thought waiting on Yair.
Yeah.
This is amazing.
Yes.
Effective.
Yeah, so it's pretty amazing, right? You can discriminate between 10 milliseconds between this in the sniff phase cycle, and that's their main conclusion. One of the first main conclusion from this article. So now after they checked actually the response to the optogenetic stimulation in the sniff cycle, and they saw that mice could indeed discriminate. What they wanted to check is the responses of the mitral cells, right? You just mentioned the relay station after the station after the olfactory sensory neurons. And what they used is they did electrophysiological measurement. They used 16 or 32 silicon probes in the mitral cells, and they checked how many mitral cells respond to one light evoked response, and they saw it's about 57%, and they're saying it's pretty similar to what studies show. It's about 66. So if you present order, an individual order, the average response of the mitral cells are 66%. So I think it's pretty similar, and we can another proof that the light evoked that the optogenetic stimulation holds and it's good. So just talking about one individual order and 66 cells in different different responses, significantly or not, but 66% of the cells respond to one individual order in average. So it's pretty.
One order is one receptor or
one
order?
one order, not no.
It has an
Yeah.
order.
Yeah. Okay. Okay, so they use the electrophysiological recording, and you can see here raster plots. These are raster plots and PSTH of two cells, and they again you can see here the sniff cycle, and now they wanted to see the response of the mitral cells again to different time points. So they chose 3 time points: 32 milliseconds after the inhalation onset, 62 and 92. They had 3. They changed 3 latencies or 3 time distances, and they wanted to see how the mitral cells respond differently. What they did is after the raster plot, they put it on a PSTH graph. What you see in black is the spontaneous activity, okay, and in red or here in orange you can see the light evoked response. And for each of those PSTH, they fitted a Gaussian function with 3 parameters. So the first one is the latency, which is sigma. You can see here it's 7. So the latency is after I present the stimulus. Okay, for example here, when does the peak come? So here it comes 7 milliseconds after. Okay, so this is the latency, sigma. The duration, which is tau. What's the duration of this response right after the stimulus? And the amplitude, which is A. Okay, so you have 3 parameters. You can check now what are the differences between different cells relative to to those parameters, and they saw that some cells, like cell 1, do not change significantly the amplitude when they vary the latency. Okay, so you can see there is some change, but not significantly different. Okay, you can see the amplitude are pretty much the same. And in other cells, they saw a significant change in the amplitude response. Okay, so you can see here that cell number 2, when I present after 32 milliseconds, I get a very high amplitude, but then 62 I get a lower amplitude, 92 I get much less. So there is probably this amplitude carries some information about the timing, right? You can say it's not only the timing, the latency that carries information, but also the amplitude of, again, those are firing rate, raster plots as we saw before in Yair's talk. Okay, so you have two kinds of cells, and what you see here, again, these are two cells which you can see here. This is the red and this is the orange. Those are, of course, the different cells, and the blue here is the average of all of them. So you can see some change, some not. On average, maybe there is a little decrease in the amplitude. And the next thing they wanted to check is how much, we said there is a latency, there is the amplitude, how much of these cues are really relevant, how much information they carry. Why? Because of two reasons. Why they saw that the amplitude changes, but also it's not shown here, but they checked the tuning curve for latency, and they showed that it's quite heterogeneous, meaning that if the tuning curve for the latency, how much time the peak comes after the stimulus onset, if it's very, the variance is very heterogeneous, so probably there is some kind of information to the amplitude. So they did is they used a classification algorithm in which what they did is they chose, they took 150 milliseconds of 10 milliseconds each, and they checked, they calculated the firing rate in each of those 10 milliseconds, okay, over a period of 150 milliseconds. But they aligned it differently. So for one of the in the algorithm, for one of them, they aligned it to inhalation onset. Okay, meaning to this onset here of the sniff phase, and this means that the algorithm still has the information both about the timing and the amplitude, right? If it's on the inhalation onset, but the other vector of the 150 milliseconds, they aligned it to the stimulus onset, meaning to this blue, right, to the stimulus onset, and now you still have the information about the amplitude, but you don't have any the information about the relative timing in the sniff cycle. Is it clear? Okay, so one of them carries only the timing, one of them carries the timing and the amplitude, and you can see the results here of the classification algorithm. You can see here the 32 versus 62 and the 32 versus 92. In yellow, you can see the stimulus onset. So the stimulation onset has only the timing information, and you can see here it's about 57% in this 32 versus 62 discrimination. In the 32 versus 92, it has about 70%, so it does have some information, right? It's not chance level, but when we also, I confused, I said it has the timing, it has only the amplitude, right? The stimulus onset has only the amplitude information, and you can see it's about chance level, and now with the inhalation onset, it also has the timing. You can see that it reaches over 90%, which is pretty good, right? So the conclusion is that both timing and amplitude, right, timing, latency, this parameter, and both the amplitude, the A, are cues that carry latency, the other latency, that which time in the sniff phase cycle the stimulus arrives, they both carry this information. Okay, and that's the yes.
Did you try only the timing without the amplitude?
The time without, no, I don't know how, do you have any idea how to?
Normalize amplitude and negate the timing.
You can, what do you mean normalize?
Maybe stop the trace before the peak begins.
Yeah, someone should just.
Yeah.
No, we didn't do it, so just
Yeah.
saying that.
But yeah, and just like how would you assume that the results would be like here you can check what's the right. This is only timing. This is timing and amplitude. So maybe it's maybe
Different.
yeah.
You can normalize them all to the same amplitude,
That's
then you
what
got
I
the definition.
Okay, so as I said, very straightforward, very pretty short, and this is all for the results of this article. And then they continue in the discussion, and they refer to all kinds of articles, and I found this one pretty interesting, and they talked about it, and they wanted to, we know what's the response of the mitral cells, and we checked the sniff phase discrimination, the olfactory sensory neuron, to check what are the mechanisms that underlie this temporal coding and this time resolution. So they referred to this paper from 2007, and you can hear a couple, two main things. One is that you can see the sniff cycle here, and this is LFP. You can see LFP of the mitral cells, and you can see that it's sniff locked. The mitral cell activity is sniff locked, meaning that as the sniff phase changes, also the activity, the LFP, the subthreshold activity changes, and this makes sense because the mitral cells are more responsive, very close to the peak of the inhalation sniff cycles. So this is the subthreshold, and you can also see here the multi-unit activity, the activities that they evoke the activities. Okay. Obviously, you can see that they evoke. So this is one thing to turn our to take into account that indeed there is some sniff phase lock, and what we just said, that they can assume it makes sense. And the other thing that I will just go on quickly is that you can see here the number of action potentials, and this is the latency, what we showed before. And you can see that for short latencies, it's a more stronger response, meaning the cells fire more when the latency is short, and you can see that one or two action potentials respond only in later latencies. Okay? And you can also, what they wanted to check, in this article they changed the concentration, and they said if we have stronger responses in shorter periods of time, right, after a short latency, what happens if we change the concentration, what happens to the overall latency? As we saw the PSTH is the overall activity, right, the peak, and they saw in there that when you change the concentration, it turns from low to high. You can see that the overall onset, right, the peak that we saw before in the PSTH becomes earlier in time. Okay, so this is another thing that they used those two conclusions to speculate some coding scheme, which they think makes sense, and probably not just they. So odor identity probably is encoded in the following way, that you have some temporal pattern. So you can see that if you present the same odor in different concentrations, still, if this is glomeruli, mitral cells, still the orange one fires before the green one. So there is some kind of temporal pattern which stores the odor identity or carries information about the odor identity. And on the other hand, to discriminate between odor concentration, how do I know if it was 20% of this odor or 50%? The glomeruli, the mitral cells, they check this temporal pattern, or the computational model is that the calculation is relative to the internal representation of the sniff cycle. So whether the overall activity of all of them, even though still this cell, let's say, will fire before this one, the overall latency, the overall activity of all of them, if it's earlier in time, probably the concentration is higher, and if it's later in time, probably the concentration is lower. They just showed in the article before, and that's it. Thank you.
Good. Last, did anybody here attended this seminar? Do you know when he was here? Like 6 months ago?
Before we started?
No. the mice can use only the timing from the snip cycle of the first 25 milliseconds to make a good decision. It doesn't mean that it does,
Yeah.
but it can. Yeah. Anyway.
So,
Okay.
yeah.
Whichever.
Isn't it weird claiming that the sense that it's so slow is coded by temporal code, which is so quick? I mean,
Yeah, why do we
Why
say,
do you say
why do you
it's
say
slow?
it's slow, yeah?
why? Smell, because I can smell something for a few seconds in the row, the perception doesn't change
Yeah,
for
but it
a
does,
few seconds. So what? Is
Well, I can
sequence
play a
repeating,
sound. I can
repeating
play
itself?
a sound for 10 seconds, and it will also be perceived similarly. What is slow? Slow is
But
when you can discriminate.
it's always sounds can be very quick. Orders are not quick, and naturally they're never quick, right? It's never a quick change of
You mean
order.
you're asking what,
diffusion versus the speed of light? That's
The
what
speed
you
of
mean?
sound and
Speed of
light,
light
yeah.
and sound,
Yeah,
whatever.
sure. Yeah, it's much
Yeah, but when
slower.
it already arrives to you, it
But
doesn't matter. When it
Yeah.
already arrives to your receptor, it doesn't matter.
Doesn't matter how long it took it to be there.
The
but it
question is,
stays there. It doesn't change. Why do I need temporal coding for something that doesn't change quickly? It changes
I,
on the course of at least seconds.
you can ask what's the, I don't know, evolutionary purpose of having, why is the encoding, right? Because you have some kind of chemical features in the order, and by maybe it responds because, I don't know, it reacts more, it responds more, it's more sensitive to one of the chemical, to one feature, right? And up to another, and then it reaches in different time points, and that's how you can discriminate the fact that it's this order and not another similar
The
order. So,
processing itself puts the emphasis on different aspects of the smell during the.
yeah, I mean, so I wouldn't say it's slow. I would just like, you can ask like why was it invented in such a way? But
This
think
was the
about
common intuition and knowledge in the field that odor is very slow and animals are slowly maneuvering in the environment for odor. But this was proven wrong when you just test how much time it takes a mouse to discriminate sound, uh, sight, and smells. And they can do smells as fast as they can do sounds and whether, a changing odor and on time, etc. I don't know exactly the resolution and time, but what it shows you is remarkable that you can calculate the time from the sniffing cycle. If it's x or x plus 25 milliseconds or even 10 milliseconds, you can tell the difference.
It was using an algorithm, right?
No,
no,
we use the behavioral test.
the
Oh yeah,
the algorithm
right.
was,
Yeah.
yeah, remember?
And this is what caused the whole field of Gilles Laurent's decorrelation patterns to sort of collapse. Because all these decorrelations take time to evolve. Now, it doesn't mean that there's no information there. But for odor discrimination, mice can do it extremely fast. Remarkably fast. Actually, generally performance is much better in olfaction than in other senses for mice.
My human intuition is what guides me.
Yeah. Human intuition, yes, sure.
I have a general question regarding those two articles. Why didn't they use a negative that are the negative? They it was just preventing water and not. So what is the logic behind that?
don't know if it's a satisfactory answer.
Also, they did have some kind of a punishment, which they changed the trial interval.
Their punishment is they paused the